Okay, yeah, thanks for the nice introduction. So it's always a pleasure to be back at CWI, even though it's remotely, I guess. So yeah, keep in mind that I cannot see the chat. So if you have questions, feel free to either just interrupt me or maybe Job or someone else can relay the questions. So today I would like to talk about a topic that I'm very interested in. It's mutually unbiased bases and an approach based on polynomial optimization and symmetry. So basically here on this slide, I gave you two pictures. So the left would be an example of two unbiased bases, let's say in the plane. And on the right, I sort of gave you a picture of what symmetry reduction is going to be. So we start with a big matrix or matrix algebra. That's this orange block here on the left. And what we want to do is we want to make this algebra a lot smaller and get like nice small blocks that make it easier to compute things. So this talk is based on joint work with Sven Polak, who's currently at CWI, even physically, and he's also in the audience. You can find it also here on arXiv if you're interested to know more details. Okay, so the first part of the talk will basically be about mutually unbiased bases and what is known. And the second part will be about symmetry reduction and our contributions. Okay, so let me first give you, let's see if I can go to the next slide. Yes. So let's start with the definition of what are mutually unbiased bases. So we say that a set of k orthonormal bases of CD is mutually unbiased if whenever you take two vectors from distinct bases, you have that the squared inner product is 1 over the dimension. Okay, so this is a very easy to state property. And it's also not too hard to construct mutually unbiased bases in certain dimensions. So on the first slide, I already showed you a picture of two mutually unbiased bases. There were the standard bases and the Hadamard bases, so the 1, 1, and 1 minus 1. And it's easy to see that if you would take a vector, for instance, the first vector in this basis, the first vector in this basis, and you look at the squared inner product, then this is exactly equal to 1 over 2, right? Which it should be also according to this, this definition. Okay, and then in dimension 2, you can find a third basis that is also mutually unbiased to the first two. And it requires to use complex numbers. So you can use I1 and 1i. So for the quantum people in the audience, you might also recognize them as the eigenbases of the Pauli matrices. Okay. So here I've given you 3 mutually unbiased bases in dimension 2. And a very natural question is now, what is the largest number of mutually unbiased bases you can find in a given dimension? So that's sort of the motivating question that sort of inspired this work and this talk. Before I want to go into what is known about the largest number of constructions, let me just briefly give a pointer to a very nice survey on mutually unbiased bases. It's also the title of the survey. It's a very long survey, but it contains many nice constructions. And if you're interested to learn more about such bases, I would highly recommend this survey. So just a brief word about why MUPs are important for quantum information theory. So you can imagine that if you are in, let's say, a crypto setting, then it's nice to be able to construct an object such that if another party measures this object in the wrong basis, they just get a uniformly random outcome. And this is precisely what happens with MUPs. So if you would prepare a state in, let's say, a first basis, and you measure it with respect to a mutually unbiased basis, you get a random outcome. So that's a nice property. And they're also so useful for many other tasks for which I would like to just refer to this very nice survey. Okay, so then what is known about this largest number of mutually unbiased bases? Well, let me first mention the only known upper bound on this number. This upper bound is dimension plus 1. And it's a very easy to show upper bound, so I thought I would just show it to you. So how do you do it? You do some dimension counting argument. So let me first define this map that takes vectors to matrices. So for instance, later we'll only apply it to unit vectors, and then this will be a map from unit vectors to traceless Hermitian matrices. So you take a unit vector E, for instance, you map it to the rank 1 projector, and you subtract a suitable multiple of the identity. So it becomes a traceless Hermitian matrix. And the nice thing about this map is that if you apply it to an orthonormal basis, so sort of for each of the vectors in an orthonormal basis, and you look at the span of the output, then this is a d-1 dimensional subspace of the space of traceless Hermitian d by d matrices. And this is not the only nice property of this map. It's also very easy to check that if you start with two vectors u and v, you apply this map, you take the trace inner product of the outcome, then this is just the squared inner product -1 over d. Okay, so this is just a straightforward computation. But the nice thing about this formula is that if you would apply this same map to MUPs, then you actually get orthogonal subspaces, right? Because the MUP condition was exactly that this right-hand side here vanishes. Okay, so MUPs are being sent to orthogonal subspaces. And then just by counting the dimension of this space of traceless Hermitian matrices and dividing it by d-1, you get that there can be at most d+1 MUPs in dimension d. Okay, so that's the only known sort of universal upper bound that we have. And sort of in light of this easy upper bound, I'll just sometimes for ease of I'll just say that such a set of d+1 MUPs is complete. Okay, so now let me mention some constructions of MUPs, or at least when they exist. So complete sets are known to exist whenever the dimension is a prime number. So this was shown by Ivanovic, or when the dimension is a power of a prime number. So d is p to the n for some prime number. And in fact, these are the only cases where we know of complete sets of MUPs. Okay. And if you see this for prime numbers and powers of prime numbers, it's very natural to expect that somehow finite fields play a nice role in these constructions, and somehow in some way this is I think very often the case for these constructions. Okay, so for me, when I see something holds for prime numbers and prime powers, I immediately think, well, for composite numbers you should be able to take some sort of product and things should work out, right? The thing is, this doesn't happen exactly. What you can do is if you have k MUPs in dimensions d1 and d2, then you cannot produce k squared MUPs in the product dimension, but you can only produce k MUPs in the dimension d1 times d2. Okay, so this the construction that one would have in mind is that you take your k bases in dimension 1, let's call them u1 up to uk. And you have your k bases in dimension d2, v1 up to vk. And then to create k bases in dimension d1 times d2, you can take the tensor product of ui and vi. So sort of for each of the pairs in these bases. Okay, so this would construct k MUPs in dimension d1 times d2. But you cannot, for instance, combine u1 and v2. If you would add that to this construction, this would not be mutually unbiased with the first k that you've just constructed. Okay, luckily this is not the only type of construction that one can make. So you can also look at something called mutually orthogonal Latin squares, which is more of a combinatorial object. You can also use those to construct MUPs. So I'll not go into any detail about these objects, but I just want to mention that this sometimes gives slightly more MUPs than this tensor product construction. So for instance, in dimension 26 squared, you would get 6 MUPs instead of the 5 that you would expect from taking this tensor product strategy. Okay, and then there's another nice result that we know that it's actually either d+1 or at most d-1, the largest number of MUPs that one can find in a certain dimension. So in other words, what Weiner showed is that if you have d MUPs in dimension d, then there also exists d+1 MUPs. So somehow the only, like the orthogonal space that we had left a few slides ago actually corresponds to another orthonormal basis. Okay, so as I said, no complete sets of MUPs are known when d is not the power of a prime number. But in fact, for dimension 6, the first such dimension, it is somehow widely believed that no more than 3 MUPs exist. That's far less than let's say 7. But there's no formal proof. So there have been a lot of works on trying to find mutually unbiased bases, like numerically. But these somehow all seem to get stuck at 3 MUBs. And there are also quite a few results actually that say for this specific family of 3 MUBs, you cannot extend it to a set of 4 MUBs, but they're not completely general. So there's no proof that you cannot find 4 MUBs in dimension 6. So for those of you who are familiar with finite geometry, there's sort of a similar picture going on there, which also has to do with finite fields, I guess. So this is also a bit too connected to one of the very nice talks that Maris gave last year. So he talked about using finite affine planes to construct MUBs. So here's a picture of a finite affine plane. This one would be of order 3, which means that there are 3 squared many points. And so this is a finite geometry, which means that we've defined a set of points and a set of lines. And for a finite affine plane, the property is that there are sort of classes of parallel lines. So for instance, here, the 3 horizontal lines would be parallel because they do not intersect. And in this picture, there would be 4 such classes. So let's see. So there are the horizontal ones, the vertical ones. Then there's a diagonal, which is sort of taken, I guess, modulo 3. So you would end up back here. So this would be a straight line in some sense. And then there are another class of lines that goes in the other direction. Okay, so there are 4 classes of lines with the property that any pair of lines from distinct parallel classes intersect in exactly 1 point. Okay, for these objects, basically the existence question is very similar to MUBs, or when they are known to exist. So it's also known that they exist if D is the power of a prime number. But here we know something much more. So there's this nice theorem of Bruck and Reiser, who showed that if the dimension is 1 or 2 modulo 4, and it's not the sum of 2 squares, or squares of integers, then there does not exist a finite affine plane of order E. So in particular, this implies that no finite affine plane of order 6 exists, because 6 is not the square of the sum of 2 squares of integers. Okay. So you might hope for a similar theorem for mutually unbiased bases. I think it would be great if such a theorem would be known, but sort of if you would apply similar techniques as the Bruck and Reiser did, then you get only a very weak analog. So you get that you cannot find MUBs where basically all the rank 1 projectors have rational coefficients in this sense, that the real and the imaginary part are rational. For all the basis elements. Okay, so this is very far from satisfactory, I would say, because you would like to just put here R instead of Q.
Sorry, Sander, like I didn't know that this is known. So you're saying if there are rational coefficients, then you actually cannot find these MUBs in certain dimensions.
Yes, yes.
And
so
like, is this somehow obvious, or is it proved somewhere?
Yeah, it's proven in some notes of mine.
Okay.
I can share you the proof if you're interested. But okay. I find it somehow a bit unsatisfactory because you would. So somehow you can always reduce to the case where, let's say, the first basis is the standard basis, of course, and then all the other basis vectors would be like 1 over square root dimension times some complex number with modulus 1. And sort of this is saying that this complex number modulus 1 cannot be the sum of 2 rational numbers in this way.
But doesn't, I mean, because these rational numbers are dense, they, like, can't you say that by some kind of taking the limit that it also eliminates the algebraic numbers, or it doesn't work like that?
Yeah, I'm not sure, right? Because it's really talking about exact mutually unbiasedness. It's I don't think it would be enough to let's say have mutually unbiasedness up to a very tiny epsilon.
Okay, thanks.
Yeah. So the proof of this uses, let's say, MUBs with rational coefficients to build an integral solution to this quadratic equation. So that's also kind of how you can view this theorem of Bruck and Reiser. So they do exactly the same thing, in fact. So they build an integral solution to this quadratic equation, And that actually implies that D is the sum of two squares. Okay, so then you get this, the sort of the corollary that if D is not the sum of two squares, you cannot find bases with rational coefficients. Okay, so maybe this is a good place to point out that, okay, here we're talking about sums of integer squares, and later on in the talk, I'll also talk about sums of squares, but then I'll talk about sums of squares of polynomials. So these are not the same things. So let me now go into sort of prior work on MUPs using polynomials and SDPs. And basically, I want to make a distinction here between two approaches. So one would be the commutative approach, and the other one, non-commutative approach. So the commutative approach starts with basically formulating this existence problem as a question about finding a real solution to a set of polynomial equations. So what you do is you would sort of parameterize each basis vector with two, each coordinate of each basis vector with two real coefficients. So you just write it as, let's say, x plus I times y. And then the conditions of being mutually unbiased would give you polynomial equations in these variables x and y. And basically, the K-MUPs exist if and only if there is a real solution to this system of polynomial equations. And this is a problem that one can hope to tackle computationally. So you can use, for instance, the weak Nullstellensatz to try to show non-existence of such a solution by proving that one is in the ideal generated by these equations. Okay, so I only put an if here because it's not an if and only if for the weak Nullstellensatz. So there you would actually be checking for complex solutions. But still, if one lies in the ideal, then this would be a certificate of non-existence of a real solution. Okay. And one can test if one is in the ideal by basically constructing a Gröbner basis of the system of polynomial equations. Okay, so this is a computational approach, but it's not very efficient in practice. So then, a bit more than 10 years ago, there was a nice paper from Breyerly and Weigert, which sort of took a Positivstellensatz approach instead of a Nullstellensatz approach. So they formulated, they went away from the feasibility problem and made it into an optimization problem by basically promoting one of the constraints to the objective function. So you would take, for instance, the first constraint, square it, and try to minimize that polynomial subject to the other constraints in your feasibility problem. So this is an instance of a polynomial optimization problem, and that means that you can apply techniques from the literature to try to solve this. So there's the Lasserre hierarchy, which we'll also see later on in the non-commutative setting. And basically, this paper of Breyerly and Weigert showed that both of these approaches are already sufficient to, for instance, rule out the existence of 4 MUPs in dimension 2. So it's more of let's say, a proof of concept than anything useful, of course, because on slide 1 we very easily showed that 4 MUPs do not exist in dimension 2. But at least it shows some promise for this approach. Okay, the second approach, you can think of it as reducing the number of variables. So you would like to work, for instance, with non-commutative variables, meaning that you can work with your projectors as variables instead of parameterizing each of the coefficients of your basis vectors. And basically here there are two, as far as I know, inequivalent formulations that one can try to use. So the first one, which we'll also use a lot later in the talk, is from Navascués, Pironio, and Acín. So they gave a very nice C-star algebraic formulation of the problem. So they showed that there exist K-MUPs in dimension D if and only if there exists a certain C-star algebra, which I'll call a DK-MUP algebra. I'll define it later in more detail. And there's a sort of, so this would be a kind of a feasibility approach, right? Because you're looking for the existence of some algebra. And there's also, again, an optimization approach. So there's a formulation that is based on non-local games. So it is known that you can construct a non-local game such that this game has value p, that value p is attained if and only if there exist K-MUPs in dimension D. So such a game was constructed, for instance, by Aguilar and others, and it was based on quantum random access codes. It's kind of a nice formulation, but it's yeah, it's not equivalent to the one from MPA. And I should mention that they also try to use symmetry. They also try to use, but they only do it numerically. They don't do it analytically, which we will do later on. And yeah, so their formulation also uses more variables than the one from Navascués, Pironio, and Acín. And I think it's just in general slightly more complicated. So for today, we'll focus on this this first formulation. But I think it would be very interesting to try to apply similar techniques to this this second formulation. Okay, so then what do we do? Maybe it's time to finally get into that. So we revisit this the C-star algebraic approach of the MUP problem from Navascués, Pironio, and Acín, and we look at the related semi-definite programs. So it's very easy to see that these SDPs are symmetric under the action of some group. It's the wreath product of two symmetric groups. And what we do is we give the symmetry reduction of these SDPs, meaning that we start with the very big SDP and we break it down into smaller blocks. And the main contribution, or the main technical contribution here, is sort of a representation theory result. So we look at certain modules for the wreath product, and we show how to decompose them into irreducible modules. So I just put some words here in quotation that might be familiar to people who know the representation theory of the symmetric group, for instance. Okay, so what this allows us to do is we can compute higher levels of the hierarchy than Navascués, Pironio, and Acín were able to do. So in fact, in their so this 2012 article is actually a chapter in the handbook of polynomial optimization, and they said that they tried to compute levels of the hierarchy, but they couldn't really get very far. So we managed to go a bit further. Unfortunately, we still don't show that there do not exist 4 MUPs in dimension 6. What we do obtain is sort of or what we reprove is using sums of squares techniques, that there do not exist d+2 MUPs in dimensions 2, 3, 4, and 5. Okay, so again, this is just a proof of concept. It's nothing new, but it's kind of nice that it follows from this approach. Okay, so now let me actually get into this formulation of Navascués, Pironio, and Acín. So they sort of went from the geometric picture of trying to find vectors in CD to an algebraic formulation. So they went from unit vectors to rank 1 projectors, and then they looked at the algebra generated by these objects. So more formally, what they would do is, so suppose you're able to find k MUPs, and let's say that these unit vectors describe these k MUPs. Then you would build for each unit vector the associated rank 1 projector. And this gives you a set of projectors xij. They're d by d projectors. So I here runs in d and j in k. So I'll always use the first index to denote the basis element and the second one to denote the basis. And then you just look at what relations are satisfied by these projectors. Okay, and then we write them down, and this is what we'll use to define a C-star algebra, this, the DK MUP algebra. Okay, so we say that a C-star algebra A is a DK MUP algebra if it contains self-adjoint elements or Hermitian elements xij that satisfy 4 relations. The first relation here tells you that if you look at a single basis, let's say basis J, and you look at projector I and projector I prime, then they're orthogonal if I is different from I prime, and it's a projector if I is equal to I prime. The second condition is just that the elements from a single basis form a POVM, or a PVM, I guess. And then the third condition is actually the nice condition that corresponds to mutually unbiasedness. So it says that this degree 3 monomial, so where you sandwich xi prime j prime by xij from the left and the right, it's equal to 1 over d times xij. Okay, and if you would write this out with this formulation, basically what you would get here in the middle would be exactly the squared inner product between uij and ui prime j prime. Okay, so this is what you use to show this or the validity of this third equation. And then there's another fourth condition, which is maybe which is actually kind of similar in spirit maybe to how you derive this this third condition. So it says that if you look at any word in your algebra, so words u and v, for instance, and you sandwich u with xij from the left and the right, and you do the same for v, then these two things commute. And this is essentially, again, boiling down to if you would work out this product, you would basically get uij on the left, uij dagger on the right, and in the middle there's just some scalar, right? It's just a product of some inner products. So, and this is saying that you can permute these scalars. So you can swap the word with u in front with the word with v in front. Okay, so these relations together define this this DK-MUP algebra. And then in what I find one of the most sort of the nicest results about C-star algebras and polynomial optimization is that they actually show how to characterize MUPs using this. So they show this if and only if that K MUPs exist in dimension D, if and only if this DK-MUP algebra exists. And sort of the thing that I want to emphasize here is that this can be an arbitrary C-star algebra. It doesn't have to be an algebra of D by D matrices. So that's the very nice thing here. So I'll sketch on the next slide how they prove this theorem. But let me first mention that sort of the approach that we would take based on this theorem is we try to show non-existence of MUPs by proving infeasibility of STP relaxations of this MUP algebra. Okay, so that will be the approach that we take later on.
Sorry, Sander, in this last condition, like, is it in any way possible to make it finite without saying for every u, v in this, algebra?
Yes. Okay. Very good. Yes, you can make it finite. You can restrict to u and v of degree 3. So this would give you a finite set of relations. Yes.
Okay. Thanks.
Yep. Very good. Okay. So let me also maybe immediately highlight why degree 3 is sufficient. So let me give a sketch of the proof of this nice result. So here I've just recapped the relations that define this MUP algebra. And basically what they do is they start with let's say a C-star algebra that satisfies these relations. And now, as I said, they don't have dimension D, and so they're not D by D matrices. If they would be D by D matrices, we would be done. Okay, that's something that you just have to trust me on for the moment. So what they do is they start with, let's say, these xij's, and then they construct zij's, which are D by D matrices. Except that their entries, they're D by D matrices whose entries are from the C-star algebra A. So they're not yet really D by D matrices with complex entries. Okay, so the way they do this is they sandwich xij with let's say xa1 and xb1 from the left and right. So A and B would run in the interval D here, and then they put x12 and x12 on the left and the right. Okay, and the fact that there's a 2 here and a 1 here is just you pick something arbitrary as long as they're not the same. Okay, so if you construct these matrices Zij, you can pretty straightforwardly show that they satisfy the first and the third condition of this MUP algebra, just using the same relations for the xij's. So as I said, we're almost done now because we have D by D matrices, but their entries are from the C-star algebra and not yet complex numbers. But then what you do is you use this fourth relation. So you use this fourth relation to show that, in fact, all of the entries of these zij's, they commute. Okay, so if you pick any I and j and another I prime j prime, and you look at your favorite 2 entries from these matrices, these would commute. So that means that if you restrict yourself to the C-star algebra generated by these entries, you actually have a commutative C-star algebra, and this you can diagonalize. Right? So you can simultaneously diagonalize all the entries of your zij's, and this would then give you your well, then you just restrict to one coordinate on this diagonal, and you get your solution. Okay, So as I said, we're going to look at this map algebra, and we're going to look at symmetries. So let me talk about the symmetry of the problem. So a set of maps remains a set of maps under two simple actions. So you can relabel the bases, but also for each basis, you can relabel the basis elements. Okay, it's fairly straightforward to see that these two actions preserve the map property. And if you look at the group generated by these two types of permutations, then this is exactly the wreath product of SD and SK. So remember, we have D elements per basis and K bases in total. Okay, so I wrote down the formal definition of this group here, but it's not too important for the rest of the talk. It's just the elements are described by K tuples of permutations in SD and one permutation in SK. And there's a group action that's as follows. And not only is the map property preserved under the action of this group, also the relations of this map algebra are preserved under sort of the same action. So you can permute the non-commutative variables by just applying this sigma and tau to the indices of the variables. Okay. So the map algebra is preserved under this property, and it then follows that also the SDP relaxations inherit this symmetry. So let me now first talk about a bit of general theory about symmetry reductions, and then I'll go into the map SDPs, let's say, and then we'll show how to decompose them. So as I showed on slide 1, sort of the picture that you want to have in mind is that you start with a big matrix algebra and you want to transform it into a direct sum of smaller matrix algebras. Fortunately, Acín and Wedderburn showed that this is possible in general. So you can always block diagonalize the matrix algebra into a direct sum of full matrix algebras, and this will typically result in a smaller representation. So how is this related to semi-definite programs? So in semi-definite programs, you also have a natural matrix algebra that is generated by the objective and constraint matrices. And you could try to use this Acín-Wedderburn theory to block diagonalize your algebra, and therefore you would also block diagonalize in some way the SDPs, which means that if you start with your big semi-definite constraints, you would be able to write them as a sum of smaller semi-definite constraints, which would be computationally very, very useful. Okay, so let me give a tiny toy example. So there's this 3x3 matrix on the left, which contains quite a bit of symmetry. So you can permute these last two rows and columns. This one is positive semi-definite if and only if this sum of a 2x2 matrix and a 1x1 matrix is positive semi-definite. Okay, it's not too hard to show this on paper, but this is sort of the general picture that you have in mind. You start with a big matrix and you decompose it as a sum of smaller matrices. So the setting that we will be interested in is where the algebra of matrices is group invariant, which means that there's a group, for us a finite group, acting on the rows and columns, or the indices of the rows and columns of the matrix algebra. And so just to continue this example from the previous slide, here the group would be S2. And like I said, it would act by permutation on the last two rows and columns. And this setting of group invariant SDPs has been used in many areas. So here are some references. I think the main area of application so far has been coding theory, but there also works in combinatorics, and it's also shown how to do this in general for polynomial optimization problems that are, let's say, symmetric under the symmetric group. So there's a nice original work from Gateman and Parillo, and also a nice survey from Riener et al. So they always focused on commutative polynomial optimization, and we'll also be looking more at the non-commutative setting effect. But the general theory remains the same. Okay, so group invariant SDPs are very nice because there's a very explicit recipe for how to obtain this symmetry reduction. So that's what I want to sketch on this slide. So we're again in this setting of Z by Z matrices that are invariant under the action of the group on both the rows and the columns. So this is just to repeat the statement of Acín-Wedderburn. But what we know additionally in this group invariant setting is what this K and Mi are supposed to be. So basically, you can obtain them by decomposing the vector space on which these matrices act. So you look at C to the Z, and you try to decompose this into smaller modules for the group. So a module for a group is just the vector space on which you've defined the group action. And what you want to do is you want to decompose your vector space CZ into a direct sum of irreducible modules. So these are just objects that you cannot decompose further. And then you collect, let's say, isomorphic terms. And these would define your K and Mi. So these would also define the size of the SDP that we're going to solve eventually. And the way to find this isomorphism that Arten Wedderburn promises that exists is basically based on this decomposition of your vector space. So if you have this decomposition, basically what you need to do is you need to select one element from each of these vector spaces. You need to do it slightly carefully, but then the isomorphism between this space and this space would just be given by taking inner products with respect to these representative elements. Okay, so that's sort of to give you an idea of what we're going to do in the rest of the talk. We're going to look at SDPs related to this MUP problem. We're going to look at the vector space, and we're going to decompose this into irreducible modules. Okay, so I think now after 40 minutes, it's time to finally show you the SDPs that are related to this MUP problem. So essentially what we do is we just follow the standard tracial polynomial optimization approach to try to show infeasibility of this, or to try to show the non-existence of this C-star algebra. So what we do is for integers d, k, and t, we define this SDP. So I'll show in a minute why it's an SDP. So the variable here would be some linear functional acting on non-commutative polynomials of degree 2t. And it satisfies a bunch of properties. So it's supposed to act a bit like a trace. It's supposed to vanish on the ideal generated by the constraints in this MUP algebra. And it's supposed to be positive. And we normalize it in this way. So we normalize it in the sense that the trace of a projector should be equal to 1. Okay, so just for those of you who've never seen polynomial optimization problems before, this is indeed a formulation of a semi-definite program, because you can capture this constraint of positivity by a positive semi-definiteness constraint on a certain matrix, the moment matrix associated to this linear functional. So you have this statement that L of P star P is non-negative for all P, if and only if this moment matrix ML is positive semi-definite. Okay, so to link it back to the general theory on the previous slide, the vector space that we're interested in is going to be basically the space of non-commutative polynomials of degree exactly t, right? Because this is our positivity condition, and if we're interested in polynomials of degree t, then these monomials would be taken from the ring of monomials of degree at most t, and so that's the vector space that we're going to decompose. So you can either think of this as homogeneous polynomials of degree exactly t, or you can think of this as a t-tuple of pairs from d and k. Okay. So I've already mentioned the symmetry of this MUP problem before, and I'm just going to ask you to believe me that these SDPs sort of inherit the same symmetry. So we have this set of indices, and the SD-SK action is defined on this set by basically doing exactly this relabeling of bases and of basis elements. So how do we decompose the vector space CZ? Well, the first very easy step in this decomposition is we look at orbits. So you can look at orbits of monomials, and this would give you a first decomposition of the vector space. And it's not too hard to show that these correspond to pairs P and Q, where let's say P is a set partition of T and Q is sort of a refinement of P. And I think I'll just show an example to sort of make clear what's going on. So consider, for instance, degree 4 monomials, and the set partition of the set of 4 elements, that is 1, 3, 4, and 2. Okay, and then the second object Q would be a refinement of 1, 3, 4, so a set partition of 1, 3, 4. For instance, 1 and 3 and 4 go together, and Q2 would be very easy because it's a set of 1 element, so there's only one possible set partition. So so which orbit corresponds to this? Well, basically it's the span of monomials whose indices are of the following form. So basically they would be constant on this set, meaning that the first, the third, and the fourth elements from K would be the same. So that's why I put J1 here. Also color-coded objects that are the same. And then Q1, for instance, would show that the first and the third element have the same I component, and the fourth one has a different I component. Okay, and if you work, if you apply, let's say, this group action on such monomials, it's easy to see that you remain of this form. So that's why this would form an invariant subspace, and it corresponds exactly to this orbit. Okay, so this would give you a first decomposition of this vector space. It's a very easy decomposition. So this is really just the first step in our symmetry reduction. The much harder step is to show how to decompose this. Oh, by the way, I called this set VPQ. So basically, this is the vector space that corresponds to one orbit. And what we want to do is we want to decompose this vector space into irreducible modules. And this is the hard part of our work. So let me just sketch it in a slightly easier setting where you only have the symmetric group. So not the wreath product of two symmetric groups, just the symmetric group. So the setting to think about would just be you have k non-commutative variables, and sk acts in a natural way by just permuting the indices. Then this decomposition into orbits takes the same form, but you just have this set P. So you just ignore the Q's basically. So just to mention, this is also relevant for the map problem, because you get this symmetry if you would just restrict your SDP to only consider monomials where all of the i's are equal to 1. Right? So all the basis elements would be equal to the first basis element. So you just look at the first basis element of each basis, and you get the same symmetry. Okay, so now we use representation theory to decompose these vectors, these vector spaces corresponding to orbits. So it's not too hard to show that this vector space VP, this orbit space, let's say, is actually isomorphic to a very well-known module for the symmetric group. It's this permutation module where the partition takes this shape, gives you this shape. So it's not too. So this is just to give you a flavor of how we decompose these vector spaces. If you don't know representation theory that well, it's okay. I'll show you just numerical results later on. But I just want to give a flavor of how we do things. So you should first show that this vector space is equal to this permutation module. And basically what you do is you would look at the assignment to the jth set in this set partition and put that on the jth row of this tabloid. And this would give you the isomorphism between VP and this permutation module. And then you just look up your favorite yellow book. In this case, it would be the one from Sagan about the representation theory of the symmetric group. So he gives you a very clear recipe for how to decompose this vector space or this module into irreducible modules. So these are the Specht modules that I mentioned in the beginning. And basically, if you look at Sagan's book, it gives you an explicit decomposition of this permutation module into irreducible modules, which is exactly what you would need. But now, of course, we're interested in the wreath product of two groups. So there you can do something very similar. So you again look at tabloids. This time it's going to be a tensor product of tabloids if you want. So for the set partition P, you would do the same. And then for each Qi, you would essentially do the same as what you would do for P. So you would look at the variables corresponding to Qi and look at the assignment to the jth set in Qi and put that on the jth row here. It's not too important to follow this construction in detail. You can just believe me that the associated action of the wreath product would basically be permute the elements in this L shape for the set partition P. And on each of the tabloids for, let's say, Qi, you would apply one of the permutations of D, but the one that you apply depends on the ith row of this tabloid tau W. Okay. So this is a very natural way to define the action of the wreath product on let's say, this vector space. But it's not the standard way one would do it if you don't have this L shape. So sort of for us, it's very important that we have this L shape, because otherwise this would not be well defined. Because here we're really looking at the sigma that corresponds to the entry in the ith row of this tabloid. And if the ith row would contain more than one object, then it's not really clear which sigma one would have to apply. Okay, so this is where we're crucially using, let's say, this L shape here. So how do we now decompose our vector space? So we basically just wrote things as a tensor product of permutation modules. So the natural thing to try to do is just decompose each of these permutation modules and hope that this gives you a decomposition of your orbit space. And if you do things carefully, then it turns out that you do get a decomposition. And then the main question is, can you show that this is really a decomposition into irreducible modules? Luckily, well, what we managed to show is that the answer is yes, they are irreducible. So what we do is we link the modules that we end up with to, let's say, the Specht modules for the wreath product. So these are very classical objects in some sense. They're, for instance, I think McDonald already used them in the 80s, sorry, the 60s, I think. He already showed that these are the irreducible modules, but these are all the irreducible modules of the wreath product. So they take sort of a similar form to what I showed on the previous slide. They are tensor products of Specht modules, but the action is very different. So that's what I want to highlight. So the action of a group element on this tensor product, you would actually permute, let's say, the legs of this tensor. Right? So you would permute the xi's, and then you would just apply sigma I. Okay, so this is very different from what we had on the previous slide, where you do not permute the vi's, so you keep them in the same order, but you permute, let's say, the sigmas. Okay, and the reason that we're able to do this is this L shape. Nevertheless, we managed to show that the decomposition that we end up with, the smallest objects, are actually isomorphic to these Specht modules. Okay, so then we know that they're irreducible. So we link it to the literature in one extra step. So we also show that this space VPQ is actually isomorphic to what was previously already called in the literature the permutation module of the wreath product. So it's very analogous to these Specht modules, which I realize I've also not properly defined for you. But sort of these permutation modules are well studied also in the wreath product setting. But as far as we know, it's only known what the multiplicities of, let's say, Specht modules are for these permutation modules. The explicit decomposition of these objects, well, as far as we know, it's not stated anywhere explicitly in the literature. I'm sort of hedging a bit here because I put not so easily. We've looked hard, we couldn't find it. And yeah, finally, the construction that we give is quite natural, I think. Okay, so then so what about results? So we have some numerical results. So here I'm showing just the case of, let's say, the full symmetry, so the most powerful symmetry reduction. In the paper, we've also done this case of just the SK action as sort of a warm-up. Okay, so what do we obtain? So we, first of all, you can just describe what are the sums of squares of the block sizes. So they just correspond to the dimension of your algebra, and you can yeah, connect that back to these pairs P and Q. And actually, if you look on the online encyclopedia of integer sequences, you can find this sequence there. So what I've stated here is that if D and K are at least 2T, then this number of set partitions, of pairs of set partitions, is independent of D and K. So this is very easy to see if you, yeah, it's very easy to see. And if you look at this sequence for D and K at least 2T, then it corresponds to this sequence in the online encyclopedia of integer sequences. So this is just to show you that this number of orbits, let's say, grows very fast. Nevertheless, for let's say small D and K, we do manage to show, we do manage to actually compute the symmetry reduced SDPs. So here I've shown a very big table, so let me go through it very slowly. So the first 3 columns just define the parameters of the SDP, so D, K, and T. You can see that we go from, let's say, the 2-4 case where we show infeasibility at level 4.5, all the way to the largest case that we've been able to compute so far, the 6, 7, 5.5. And then I've shown a column with the original size of the SDP. So before symmetry reduction, this is the number of rows in the SDP. It's just given by D times K to the power T. So as you can see, this is very infeasible to compute without using symmetry reduction. And then the next columns all correspond to what happens after symmetry reduction. So this column here shows the number of real variables that are left after, let's say, taking into account the symmetry on the linear functional. And you can see that this stays very reasonable even for the largest levels that we've been able to compute. Then these 2 columns here sort of indicate the size of the SDP that we end up with. So we show here both the sum and the maximum of the block sizes. So typically the maximum of the block sizes is the, let's say, the limiting factor for whether you can solve your SDP on a computer. And this stays relatively reasonable, but it does grow quite quickly at the end. So there's still a limit to what we can compute. Then there's one column that I skipped, and this is this column of linear constraints. So after we finished our article, we talked a bit to Stefano Pironio, and he pointed out that actually we might have been missing a few linear constraints because of the way we implemented the variable reduction part, which I haven't talked about today. And then afterwards, we've been working on sort of finding these missing linear constraints. And that's what I've shown in this column. So this is the number of additional linear constraints that we found sort of quite recently. And that's also the reason that these 2 lines are still open, because we're still computing those additional numbers. Okay, then the last column of the table shows the result of the SDP solver. And now I think I'm going to have to move your pictures to the side because I couldn't see this anymore. So basically the first 5 rows here correspond to the non-existence that we've shown for small d's and k's. So it corresponds to pairs D and D plus 2 for dimensions 2, 3, 4, and 5. And we've been able to show infeasibility. And I've also put some stars here. So these stars have a special meaning. So the first star, which you can also sort of guess already here, means that we have more linear constraints than free variables. Right? So this means that we didn't even have to compute the SDP. Just from these relations, we could already tell that there was no feasible solution. Right? So this was just a linear system with 7 variables and 8 constraints. The other double star is to indicate that with the additional constraints that we found later, it became infeasible. But without these additional constraints, it was actually still feasible. So somehow we did detect infeasibility at level 5.5 without using these additional constraints. But with these additional constraints, it already became infeasible at level 5. Okay, and then of course the main set of rows of interest would be with corresponding to dimension 6 and k is 7 or k is 4 if you're very optimistic. But unfortunately there we haven't been able to show infeasibility yet. So all the SDPs that we've computed so far have turned out feasible. if you're very optimistic, there's this last line which we're still trying to compute the extra linear constraints. So there is a hope that maybe it becomes infeasible. But I think Sven and I would both guess that you would have to go to a higher level to see infeasibility. Okay, and then I think the time is almost up. So let me just give you a short overview of what is next. So far, all the computations we've done are done on a standard desktop. And by standard desktop, I mean Sven's personal computer, which is pretty good. It has 32 gigabytes of memory, but it's not a supercomputer. So maybe that's one direction to push the computations a bit further. As I mentioned in the beginning, there's also this very nice other formulation of Aguilar and others based on these quantum random access codes. I think it would be very interesting to apply the symmetry reduction to their formulation, see if we can compute some higher levels. So just to mention once again, so they also use symmetry reduction for their SDPs, but they only use the numerical symmetry reduction, which means that they first had to write down the original SDP and then reduce it. Whereas we never have to write down the original SDP. And as you could see on the previous slide, these original SDPs are sometimes already prohibitively large. So you couldn't store them in memory, for instance. Okay, and then I just want to point out that the results that we showed about infeasibility on the previous slide were really numerical results. So we haven't tried to round them to get really analytic certificates for the reason that the only dimensions we were able to, or the only case that we managed to rule out are very easy to show by hand already. But in principle, if we would get, let's say, a positive result for dimension 6, it would still, I think, take quite a bit of work to round this to an analytic certificate. And then for the symmetry reduction experts in the audience, so there's an open question, which is, I think, mostly of theoretical interest. And that's whether the symmetry reduction can be computed in polynomial time. So this is often the case for, let's say, the coding theory problems, or for when you only have the symmetric group, you can often just compute the symmetry reduction in polynomial time. But the polynomial is something like k to the power t. So this is not a polynomial that is relevant in practice. So we've just implemented a procedure, which I think in principle is probably exponential time, but we still can compute it. And it would probably be better than the polynomial time thing for small d's in the case. Okay, and then I just wanted to highlight that once again, this L shape that we had in our modules really comes from the fact that we're working with non-commutative polynomials. So in that sense, non-commutativity really makes things easier for us, which is not something you would maybe expect in general. Okay, and with that, I would like to thank you for your attention. And if there are any questions, I would be happy to answer.